So let's get started then. So today and for the rest of this week, we'll be doing geometry. So I think geometry, so it's going to be like fairly concept heavy. So you'll notice in the problem sheets, I didn't put any problems in. I'll probably introduce a few possible problems that we can do as we go, but tonight we'll be mostly focusing on some maybe new concepts, and then we'll be building towards doing some problems after our session on Saturday. So basic rules, I think we know them all. Way to find course content, I think we know that as well. Okay, so what we're going to do today, we're going to talk about what triangles are. Secondly, we're going to talk about similar and congruent triangles. And then thirdly, we're going to talk about a few different kinds of triangle centers. So firstly, an introduction to triangles. I think we should all be pretty familiar with triangles. I hope we are, but let's just, quickly go through some important properties. So it's a three-sided polygon with three edges, three vertices. Interior angles add to 180 degrees. Exterior angles add to 360 degrees. The other thing I have listed here is the triangle inequality. So this is something that we might be familiar with already, but this is the official name for it, right? So if you take any two sides of a triangle and then add them together, it should be strictly greater than the last side. So this is in terms of length, right? So if you had a triangle with like sides 3, 4, and 5, if you took any two of those then and added them together, it would be bigger than the third one. So if you ever use this in a composition, even though it seems pretty obvious, make sure you quote it. You have to say, by the triangle inequality, or like write the triangle inequality in brackets, right? Because even though this seems kind of trivial, I've definitely lost marks for not writing it before. Okay, so then the bullet point after that refers to different length conditions we have. So scalene, isosceles, equilateral. Does everyone kind of know what these mean? Awesome. And then acute, right, and obtuse. I hope that's the same. Is that the case? Okay, seems to be the case. Then we can move on. Similar and congruent triangles. Is anyone familiar with these at all? Okay, right. So two triangles are similar if they have the same shape, but not necessarily the same size. So what this means is that the angles within the triangle, the corresponding ones, are all the same. But the corresponding sides don't necessarily have to be equal. They can be proportional. So essentially, if you take a triangle, like the smaller one, yeah, each side has the same ratio. Good job, really good job. Thanks for sharing with me. Okay, so if we took like, say the small triangle on the right side, then the bigger triangle is essentially the same triangle, but we blow it up, we enlarge it. And then vice versa. The smaller triangle is just the big one. But so they have the same ratio, which is a really good point. So I'll share my screen. Hold on. Yeah, so I'll just share my screen so then we can just go through it a bit more. Okay. Okay, can we all see this? Okay, so for similar triangles, I know some of you guys may already be familiar with this, but we want to make sure that we get all of the details and make sure that everyone knows what's going on. So a similar triangle. So here's a triangle, right? Oh gosh, this is a really ugly triangle, but please pretend that the lines are straight. So A, B, C. Then we have this side, this angle, angle 2, and angle 3. Then if we had another triangle that is similar, P, Q, R, then these angles would be the same. So C corresponds to R, B corresponds to Q, and A corresponds to P. So a really important property that we get from this is that the length ratios are going to be all the same. So what that means is AB divided by PQ is going to equal to BC divided by QR, which is going to equal to CA divided by RP. Does everyone understand that? Yeah, pretty much. So for example, if we had a triangle that was like, let's just say 2, 3, 3, okay, 2, 3, 3, then like a similar triangle would be if the lengths were like this, because you just double each length. So then the whole triangle is like enlarged by a factor of 2. Okay, I think hopefully that makes sense. And that's basically the important part of similar triangles that I wanted to go. I'll go back to sharing the slideshow. Okay, yeah. So written on the right side are a few methods of showing similarity. So you can show that 2 angles are the same, or one side is the same, one angle, and then another side are the same. And then you can also show, you can show that the sides are like proportional and that the angle is the same, or you can show that all 3 sides are proportional. And then note the third point, the third bullet point here. This is the sign that we use to denote similarity. So it's like a little curvy line. Super cute. Okay. Congruent triangles is a bit of a stronger condition. So all congruent triangles are similar, but not all similar triangles are congruent. Because for congruent triangles, you need the corresponding angles to be equal, but also the corresponding sides. And the symbol we use, does anyone recognize it? The one in the third bullet point. Can someone tell me where they know it from? Just a quick recap. Does anyone want to tell me in chat, or like, yeah, it's kind of like the similar thing, but yeah, it's like a similar sign on top of an equal sign. So it's actually like really similar to the congruent notation that we use for modular arithmetic, right? But you kind of like swap the top line for like a similar one. I just think that's nice. Okay, so I think since we've gone through similar, I think we might be able to get the gist of this pretty easily. So on the right side, I have a few methods of showing congruency. And then, of course, on the left side, we have one where the triangles are essentially exactly the same. Like they are the same size, they have the same angles, they have all of that. Can an equal sign be used instead of this one? I think maybe semantically there isn't much of a difference, but in terms of mathematical notation, I think we should definitely use this one because everyone will know what you mean if you use the congruent symbol. Yeah, I would definitely just use this one. Okay, awesome. Okay, so one other thing let's just move on. So we're going to talk about triangle centers, but before we get onto that, I'd really like to talk about one thing, which is drawing diagrams. So drawing diagrams in geometry is so important because like when you have a fancy word problem, it's like, let triangle ABC be scalene, let M be this, and let B be, and let D be this point. Like you have so many random things that are all going to be put together. So that's why drawing an accurate diagram is really, really important. So that you don't want things, so you make sure that things don't get cluttered. So what you need and what you're allowed in math competitions would be 2 things. Firstly, you want a ruler. This one's only 20 centimeters, but Ideally, you might want one that's 30 centimeters. I think 30-centimeter ones are better, but this is just the one I have right now. So what I actually want you guys to do is get the stuff that I'm talking about and get paper and a pencil and then draw what I'm talking about later by yourselves, because it's actually really important. So hopefully everyone has a ruler. If not, find something with like a straight edge and then I guess try to use it. But definitely everyone should have a ruler for maths. The second thing that we need, not sure if everyone has this, but if you can get your hands on one, it would be really ideal. That's a compass. So this is what you use to draw circles. If you don't have one, then it's fine, but I think it's really helpful. Well, for math functions, you kind of do need them for geometry problems. If you don't have one for the session, it's fine. But if you can ever get your hands on one, yeah, it would be really helpful. So for these, should we go get one? Yeah, if you have one, then yeah, take 1 minute to go get one. Okay, so if anyone wants to go get one, then you guys can head off now, and I'll just wait for like a minute, I guess. Awesome, thank you for the person who told me that they have the equipment. So yeah, while we're waiting, does anyone know what these are used for, these compasses? Yeah, that's right. Oh, I can see you drawing, nice. Oh, not quite. I wouldn't say they're necessarily for drawing. Yeah, they're for drawing circles. Yeah, because you can use it. So you stab this needle part into a piece of paper, and then you can like rotate it around so that you can draw a circle. It's really useful. Yeah, it's like doing graphics, kind of like connecting points as well, like perpendicular points. Yeah, definitely. Like what you want to do with your like ruler and straight edge, your compass, these things can help you to draw some really useful constructions, because like a lot of the time you're asked for things like the angle bisector and you're like, I don't have a protractor, how can I draw that? So you just want to use these tools. Okay, awesome. So hopefully everyone has got what they need. Right, so now we can move on to some drawing and some of the triangle centers. So I'm going to be a bit naughty today since I'm screen sharing. I won't be using a compass or a ruler. I'll just be on my iPad so that I can show you guys. But definitely do get a piece of paper yourselves and draw big diagrams and as you try to follow along. Okay, so the first triangle center is like, okay, so what is a center, right? Like if we're talking about the center of a square or a center of a circle, then it seems pretty obvious, right? We can find like the middle. But then for triangle, that's a little bit different because we have so many different types of triangles. That means that we also have like a lot of possible centers, right? So the first one would be the orthocenter. So what is the orthocenter? The orthocenter is the point where the three altitudes of the triangle cut or intersect each other. So the altitude is a line drawn from the vertex of the triangle and is perpendicular to the opposite side. So we can see the line that connects point A to point E comes from A, which is a vertex of the triangle, and then it is perpendicular to the base BC. So what that means is that there's a 90-degree angle. And then what we can show here is that the three lines, the three altitudes, intersect at one point, and that's what we call the orthocenter. So I think it's more conventional, like, we'll find that something else is later labeled O, and thus, I guess the orthocenter, we can denote H. And I think that, if you ever forget how you should be labeling your centers, remember H has like, a lot of right angles in it as well. So if you're like, what do I call the like center with a lot of right angles? You just call it H because H also has right angles. That's just the way I do it. So if anyone's familiar with this already, what I want you to do right now is to prove that the orthocenter exists. So what do I mean by that? I mean prove that all of the altitudes do indeed intersect at one point. It's rather difficult, but if anyone already knows the orthocenter, then I think this is the next step. Yeah. Otherwise, let's try drawing this. Has anyone tried drawing it already? Because feel free to share, like, hold it up to your screen and show everyone. Or like, yeah, so we can just see how it's going. Okay, how about I just give you guys like 2 minutes to draw? Yeah, awesome. Oh yeah, so for 90 degrees, I think you can just like use your calculator. And like if your lines match up, then you can draw like a line across here. Oh yeah, thank you, Jackie. That's a really nice looking ortho center. Good job. Another thing that we want to be aware of. Oh, oh, Jenny, I couldn't see that. Yeah, nice, nice. Okay, so another thing that we want to be aware of is labeling things. So not we want to make sure that we're drawing the diagrams quite big because they can get messy. We want to label a lot of things. And we also want to make sure that we label like important properties or points. So it doesn't really matter which points are like A, B, D, or C, but you should definitely be labeling them in your diagrams so that you can refer to them in your proofs. Nice one. Nice one, Tara. That's really pretty. Awesome. Okay. I'll just wait on a few more people and then we can probably move on. And then if someone's still drawing, you can show me later. Yeah. But yeah, make sure you label your points, draw in your right angles. Yeah. Oh, someone's here. Oh, hi, Lena. Okay. Did I just get a message in chat? Would proving it be in relation to the area? Hmm. I mean, potentially, there are lots of different proofs that you can do for this one. So it could be a possibility, yeah. One tip for anyone who wants to check it out, I'll just send it in chat. But there is one specific theorem that I think is really useful for proving that um these points do exist. So we probably won't have time to look at it today. And I'm not sure if it's in the syllabus, but there is a certain theorem you can learn if you'd like. And it's really useful for proving that these triangle centers do exist. So if you just send it in chat, feel free to have a look at it if you'd like to. Okay, so I think we can move on from the ortho center now. Okay, so the next one is probably the thing that we see most in these problems, and that is the circumcenter. So the circumcenter is the point where the perpendicular bisectors of the sides of that triangle intersect. So what is the perpendicular bisector? It's almost a little bit like an altitude, like we said before, because the line is at a right angle to the side. But what it also does is it bisects that line. So bisect means that it splits the line in half. Okay, so then the result of that is that the circumcenter is the center O of a triangle circumcircle. So in the diagram, we can see that the circumcircle or the circumscribed circle is the circle that passes through all three vertices of a triangle. And this radius is called the circumradius. So a quick look at that, but I'll screen share because this diagram isn't the most ideal for learning how to draw it. So I'll just share that now. I'll try to draw a bit of a nicer diagram. So also one note on drawing triangles is that when we're trying different things out, we want to draw weird triangles. One thing that I always do is that my triangles always end up looking isosceles or even right angled. So then it makes me like it's quite hard to figure out a lot of properties of a certain construction because it might just be properties of like that specific triangle. So we want to draw ones that are a bit different. Are we meant to have drawn a triangle yet? Yeah, it would be good if you guys could draw along while I'm drawing right now, actually. So like as I'm doing it, feel free to do it as well. So we want to label our sides A, B, C. Okay. And then now what we want to do, sorry. Okay, is that we want to find the midpoints of each side so that we can construct the perpendicular bisector. So I'm going to be a bit naughty because I am on my iPad, but you guys need to make sure that you use the ruler to measure out where the midpoint is. Actually, I'll just put my ruler on my iPad screen. So I'll split it in half. And yeah, guys, try to follow along if you can. But yeah, no pressure if it's a bit new to you. Okay, so now that we've constructed the midpoints of each side, we want to draw the perpendicular bisector. So that is the line that comes from each of these points that forms a 90-degree angle. So what that looks like, be like, I'm trying to draw a dotted line, but failing quite miserably. And then now, oh, my diagram must be really inaccurate. Hold on. Oh, there we go. Okay, sorry about that. I've just got to adjust my points a little bit because I didn't do them very well. Okay, there we go. And then now we're going to construct the perpendicular. And then that they all intersect at one point. And that is what we call the circumcenter O. Has everyone kind of joined up to this point? I'm not quite sure what the progress is like right now, but I think I will keep on going because it should, yeah, you guys can just look at it to catch up. Okay, so now this is really cool because AO, BO, and CO are actually all going to be the same length. And when lines are the same length, what does that mean? Does anyone know what these lines are? This is what they are. They're radii, right? Because in a circle, if you have, like, let's just pick a point in a circle and just look at this visually. If you pick this point, then that's obviously not the center of the circle, right? Like this length and like any other length like that are not going to be the same. Like none of these, like these three lengths aren't going to be the same. But we already know that point O is the center of the circumcircle. So what that means is that in the middle, we have O. And we know that by definition, this is the circle that passes through the vertices. So suppose we have these points. Then AO, BO, and CO, every single one is a radius of the circle. Do we kind of see how this works? Yeah, because it's the center of the circle. The length from the center of the circle to any point on the circumference will always be the same. That's like the definition of a circle. So then what that means is that since A, B, C is inside a circle and O is the center, then all of those lengths must be the same. How do you know where to place the dots? Which dots do you mean? Like these ones? Or do you also mean like, oh, like A, B, C? Oh, okay, so this is the thing, right? This is actually true for every single possible triangle that you can possibly think of. And I'll show you guys why right now. So one really cool platform that we can use is GeoGebra. And then we can see how for every single triangle that you can possibly draw, this will always be true. So let's just draw a triangle here. It can be any single kind. Now we construct the perpendicular bisectors. Yeah. Notice how those three lines go through the same point. Okay. I'll draw this point to make it clear. I guess I'll label it as well. Instead of D, we'll call it point D. We'll call it O. Okay, nice. So we see that if we move this around, these three lines will always intersect at the same point. If anyone is already quite familiar with this, you can prove it. Yeah, you can prove that they intersect at the same point. And that would be your exercise. But look, no matter what, these three perpendicular bisectors always intersect at the same place. Now, let's draw a circle that goes through 3 points 1, 2, 3. Now, it would be the exact same circle as if we were to draw a circle with a center, like with a center O and a point on the outside B. So it's actually the same circle. Nothing changes here. And then you might be like, wow, like, does this configuration always hold as well? Like, does the circle always go through all 3 vertices? The answer is yeah. Wow. So no matter how you draw it, the orthocenter will always be the center of the circumcircle. And then you can see what happens as the triangle gets more obtuse at B. The circle actually becomes like a line. But yeah. Does that make sense? So it does work for every single triangle possible. Awesome. Okay. I think we can move on from this one now. And hopefully your diagrams were all right. What's the difference between, sorry, I didn't see your message before. So what's the difference between this and the one we did before? Oh yeah, good job, Jackie, with the radiuses of the circle. Yeah, I didn't see that. So the difference between the one that we did before and the one that we just did would be like the placement of the lines, essentially. Because do we just freehand the circle on paper? Oh no, I wouldn't do that, because you have like a compass, right? And we know that those 3 things are all radiuses, and we know the circle center as well, because that's what we constructed. So what you do is you put the point of your compass on O, the center that we drew. Now you increase the length to like OA or OB or OC, right? Because this length determines the radius of the circle. And then you just rotate it around. And then it should pass through all of them if you've drawn the diagram accurately. So the difference in constructing this is just where the bisector is. Because for the orthocenter, how do we draw the perpendicular? Sorry, not where the bisector is, where the perpendicular is. Because for the orthocenter, how we draw the perpendicular is by taking the point above and then drawing it down directly, like downwards, so that you get a 90-degree angle. It only lines up with B and C ends. Yeah, sometimes diagram drawing can be a bit hard. Yeah, don't worry. I think it will get better with practice. Just make sure your stuff is big. You're like trying to, because it's quite easy to, be slightly off and things like that. But yeah, it's okay. Yeah, so for this one, the perpendiculars are the altitudes. They're like the feet that drop down. So this is a really important definition. It like drops down from that point. So can we see here how from A, you like kind of drop down onto BC so that you have a 90-degree angle. But then for the next one, the image that I've chosen isn't like the one that shows this the most clearly. But what you do is instead you start from the midpoint of the sides, then you go upwards instead of dropping down. Does that make sense? If you guys want some more explanation on that, I can probably like draw them like next to each other later and then kind of show you guys how it works. But yeah, maybe the next one will be a bit easier to draw. So let's move on to this one. Next is the centroid. So centroid has a lot of interesting properties as well, but I would say that we don't see it as much because it just isn't seen as much because we're always seeing like the circumcircle, but centroids don't come up in as many of the problems. Yeah, but it's where the three medians of a triangle intersect. So median is a line that joins the midpoint of a side and the vertex of the opposite triangle. So compared to the previous one, the circumcenter, instead of constructing the perpendicular, we connect the midpoint to the vertex opposite. So I'll share my screen again to depict this. Also, if anyone wants to like message me or something, ideally could you message the person called Nicole, because otherwise I can't really like see right now because I'm sharing screen. I can't see the chat sent to the MINDNZ account. Yeah, okay. So the centroid. I think the centroid is probably one of the easiest to draw, sorry. So you have a triangle A, B, C. Then you want to find the midpoint of each side. I've kind of eyeballed it a little bit, but hopefully they line up. Okay, these line up really well. So what we've done is we've split up each side. So here's a bit of notation as well. When you want to say that sides are equal, then you kind of like draw lines through them. So this means that BD and DC are the same length. And kind of similarly, we can use different numbers of lines. So we could do 2 lines to show that AE and EC are the same. And finally, we could do 3 lines to show that AF and BF are the same. So yeah, let me know when you guys have drawn the diagram. Feel free to show me. So the interesting property of this, I think, is how you get the medial triangle. So the medial triangle is this little triangle inside. So these triangles are actually similar. For anyone who wants to know, DEF, also this is the way we can notate triangles. What I do is I draw a little triangle and then I write the letters that outline the triangle. In that case, it's DEF. So DEF is actually like it's similar to A, B, C. So it's actually a dilation. Yeah, but we don't need to get to that. Sorry. So I'll just give you guys 2 more minutes to draw the diagram. Sorry. What's DEF called? Oh yeah. It's called DEF is the medial triangle. But I don't think it's too important, but yeah. It's just like something cool that we can kind of get out of it. Sorry. The point of this one, I guess it depends on the problem because all of these centers do have a lot of interesting properties. Like they have so many properties that it's kind of hard to gauge which ones. The main thing with this, I think for now, is probably just length ratios. Like you know that these lengths are the same, these lengths are the same, these lengths are the same. And that's probably the most important property for now, I think. And also with the medial triangle, we can actually show, oh, by the way, we call the centroid G. G is actually also the centroid of the medial triangle, DEF. So, I'm going to draw this in a different color so we know that they aren't the same lengths. But it actually splits up each of these sides as well, which is really cool. Okay, has anyone drawn it? Yeah, it looks awesome. Is that some color coding? Nice. Wow, really good, guys. It's all looking really good. Yeah, awesome. Cool. Okay, so I think we can probably move on from this one then, since it's going pretty well. Oh, some people have... Okay. I'll share again. So we can get to the last triangle that we have left. Okay. Also, guys, are you finding the pace of this all right? Like, it's mostly just some introductory content. So, what do you all think? Yeah, hopefully everyone is keeping up and not finding it, too hard or too easy. If you guys are finding it too easy, then definitely do try to do like the extension problem I gave before, which is like prove, well, not just the extension problem that I gave before, but prove that you can try proving all of these centers that like prove all of them actually exist. So when I ask you to prove them that they exist, I'm asking you to prove that all of the three lines that join to make the side intersect at the same point. Yeah. So let me know if anyone does want to do that, but I'm not getting any response on that yet. Okay, so the final center that we're going to go through today is the incenter. So the incenter is the point at which the bisectors of the interior angles meet. It is the center of the incircle. Okay, that might be a lot of new terms. So what does bisector mean? It splits it in half. So it's the line that goes through an angle and splits it in half. Is G the center of both triangles or just medial triangle? G is actually the centroid specifically. It's actually the centroid of both triangles. Yeah. Awesome. Okay, so the incircle, I'm going to share my screen once again so that we can talk a bit more about this and how to draw it. Because in order to draw, sorry, in order to draw an incircle, we need to draw angle bisectors. And angle bisectors, you need a special kind of way of drawing them. Okay. So we have a triangle. A, B, C. Then, so this is how we notate angles, by the way. If we wanted the angle at B, then we could either say just this little angle sign, B, Or we could write A, B, C. So it's essentially going from like A to B to C. So then you kind of get this outline, which is like that. And then therefore it means this angle. So in this notation, like ABC would also be equal to CBA. So you just want the angle at the middle point. Not the middle point, but at the letter in the center. Right. So what we want to do is bisect this. So we want to split this angle into half. So look, like visually, it's really hard to get it accurate, right? It's like, where is it really? Because we have to split these into two equal angles. And that's really hard to do without a protractor. So there is a really clever method of doing this with your compass. So does anyone already know how to do it? Okay. Oh, good job. Good job. One person does. So I'll go through it quickly for those who don't know, because it's quite a good skill, actually. And I think that I didn't even learn it for a long time. So what you want to do with your protractor is put the needle part on B. Then you set a certain length with the protractor. You can do any length you want, but probably something around this long. Then you draw a circle. Or you can just draw part of the circle, but you want to find these intersections. Okay, I'm just gonna make that a little more accurate. So this is essentially what you want to get. Now you take these points and then you draw something with a reasonable radius and the same radius for both points. So you want to draw like another circle from there. So you could go like that. This is a little ugly, but and that. So that these radiuses are the same. So you want to put your compass on this point. Let's call it M. Then you draw a little circle part. And then now you put it onto the next point, N, using the same radius. So don't change how like far your compass has like stretched open. Just keep it the same. And then you draw a little circle there as well. So the important thing is you want to choose a radius so that the circles will actually overlap or intersect each other. And then if we can get to that point, now we want to look at the intersection, then connect it with B. And then that will be the angle bisector. So I think it's a bit of a complex process, but once you get used to it, then it does make a lot of sense. If anyone has drawn an angle bisector, can they please show me? Um, oh, yeah, nice one, Tara. Who's that, Jackie? Oh, yes, nice as well. Very good job, guys. Oh, yeah, nice, Sally. So that's how we draw the angle bisector. Now, the annoying thing is kind of, we have to do this 3 more times. Well, or no, sorry, 2 more times, or at least 1 more. Since we know that the angle bisector does exist, then we can just do it 1 more time. So let's just do it 1 more time, say at A. Just for practice, maybe we can do it a bit more quickly this time, since we're all, quite good at it now. And then we know that it will also be true for the last one. Now, all of these angle bisectors will intersect at one point, the incenter, which we call I, which is a bit more intuitive. I think it's helpful. So hopefully your drawings are going all good. Okay. In what scenario would we need this? Like, what kind of question? Okay, how about I just find one? Yeah, I'll just find one. Honestly, there are lots of possibilities, like, because geometry problems, they can just, I guess a typical Olympiad problem is like, they give you certain conditions. So they're like, a triangle with incenter, this, like, incenter, I, and incircle K, like, intersects, like, this line from some certain place. Like, so what it's doing is it's kind of telling you what diagram to draw. So you need to know how to draw the diagram. Then at the end, yes, nice, Tara. Then at the end, what it will probably give you is something for you to prove. So it might ask you to prove that these 2 triangles are similar, or it might ask you to prove these 2 lengths are the same, or these 2 angles are the same, things like that. So the most important part, and why I'm teaching you this, is so that you know how to draw the diagrams and actually set up the problem. So I'm actually going to try to see if I can find like one, but all my example problems are probably a little hard and have to use other skills as well, which we'll go through on Saturday. But yeah, let me just find one. Okay, so one problem could be let the incircle of triangle A, B, C have center I and touch A, B, B, C, C, A at P, Q, and R respectively. Prove that, so this is usually the thing that they want you to achieve, right? So they give you an initial condition and then they ask you to prove something. Prove that the area of triangle ABC is given by RS, where R is the radius of the incircle, and S is the semi-perimeter. So a question like that, does that make sense? So usually it's, yeah. So they would give you something, so you need to draw a bunch of things like the incircle or the circumcircle, and then they would ask you to show that something's true. That's how it works most of the time. Okay, so hopefully everyone has drawn their little incenters. So I'm just gonna do this. Usually you want to draw your diagrams using pencil so you can rub things out. Sometimes I don't, when I know that like the diagram isn't that hard. But if you're drawing like a bunch of like construction things, like drawing a bunch of little circles just to draw like an angle bisector, then you want to draw those with pencil so they don't clutter the place and you can rub them out. Okay, so now that we have our point I, we can do all sorts of interesting things with it. One of them is what happens when we drop the foot. The foot, by the way, refers to like the foot of the altitude. So I'll just quickly explain this terminology. Here we have A, B, C. Here. Then this is the altitude, this line that forms a 90-degree angle. And this is the foot, E. Oh, why did I use E? I'll just use D. Makes a lot more sense. But yeah, so what we want to do is drop the foot from I to all of the triangle sides. So we take the point from here that goes onto AB and forms a right angle. Let's call that D. We drop it again. We can call that E. Then we drop it one more time. Oh. And we can call that F. So all of these should be 90 degrees. Now, we have a little triangle, DEF, that is in the inside. What's really cool now is that I is, well, the circumcircle of this little triangle. So what that means is the triangle centered at I will pass through all of these. My diagram isn't the most accurate, but it should be, it's true. It is how it works, even though my diagram isn't working out right now. Yeah. Okay, no, the circle's too good. I'll just have to draw it by hand so I can show you what it's kind of supposed to be like. Okay, so now this is my circle. And that's the circumcircle of the smaller triangle, DEF. And this is what we call the incircle, because the circle is inside of the triangle. So is that how we show if it's true? No, this isn't how we prove that it's true, but this is a property. Yeah, this is an important property. So if you draw a circle with center I and IE or DI or FI as radii, then it is the incircle, so the circle inside the larger triangle And does anyone know what a tangent is? Can someone tell me? Does anyone know what a tangent is? Not quite. It's where one point. So nice. So one point. It's where one point of a circle touches a straight line. Yeah. So what it means is a tangent line is a circle. It's not a circle. It's a line that touches a circle or something else at only one point. So here we have the circle center. The tangent line is perpendicular to that. Has to meet two edges of the circle. Also has to be straight. Close. I wouldn't say that it meets two edges of the circle. I would just say that it can only touch the circle once, right? Because, like, let's take a look at this. Oh, that is not a circle. Here's a circle. Here's a line. That is not a tangent, right? Because it touches the circle at 2 points. This is also not a tangent because it touches the circle at 2 points. A tangent line to a circle is a line that only touches the circle at 1 point. So a line like that, a line like that. Do we get what that means? Does everyone kind of get what a tangent is now? So now this might look a bit familiar because lines AB, BC, and AC, the sides of a triangle, the sides of this triangle, they're all tangent to the circle, to the incircle, because they only touch it once. AB only touches the circle at D, BC only touches the circle at E, and AC only touches the circle at F. So that's a really important property. There are a few more, but I don't think we have time today. And they're, these ones are the most important ones, I'd say. So I think we can probably wrap up here.